Bootstrap. So it's my privilege to introduce to you guys George Zweig. He was all this time a legend to me. And I first met him September last year, and you know, you don't have legends appearing in front of your eyes. So I worked hard, and finally he's here for all of you. Now, George really has a very illustrious and peculiar career and life. It could be a movie story. He was actually born in Moscow, but with Austrian parents. But his family, his parents and him moved to the US when he was 1 year old, right before it's too late. Okay. So he grew up in Michigan, in Detroit, and went to Michigan University, receiving a math degree in 1959. Actually, he said he knew Sam Ting from that time. I think Sam Ting had the double major, right?
He wasn't math.
I think that's what I read. Both physics and math, whatever. So he then went on to Caltech and received his degree in 1963. Actually, 3-4 years later, he became full professor at Caltech. But in between, he did, you know, the thing he's going to talk about today, this famous and infamous quark work, okay, which truly had affected his life, right? So after he became a professor at Caltech, he, among other things, started to migrate towards neurobiology. I joke saying cutting off cats and picking on their brains and so on. And you know, he developed a great interest on hearing, understanding the cochlea, and developing sound recognition algorithms and so on. Another part that affects his career. So neurobiology, sound, and you know, getting signal out of noise. He later on, in relation to this, founded an algorithm company called Signition. I'll come back to that. This will be a long introduction. Not to torture, but I think people may be curious, and because it's so peculiar. He got into trouble, if you were here Thursday last week, he got into some trouble with the provost of Caltech. So in 1981, he moved to Los Alamos. I would say at a relatively low pay scale, whatever. He stayed on there for about 20 years, and then moved East Coast for personal reasons. And after some while, he got into Renaissance technologies. Now, this was also new to me. I didn't personally care about the Renaissance technologies. But first of all, it's sort of the best hedge fund company in the United States. Very renowned, making a lot of money. You know, hedge fund is 对冲基金，就赚别人家钱。Actually,
the microphone doesn't work.
Yeah.
No, it's too sensitive. Hope this one works better. This one's better?
Yeah.
Okay, should I start with this one? So, I'll jump aside a little bit and introduce Renaissance. Everybody has heard about Chern-Simons.
Yeah.
Some of us have heard that Simons became rich. He even became philanthropic towards physics. The Simons of Chern-Simons is the founder of Renaissance. He's a much richer man, I think, than George Zweig, but very special human beings the same. So this is, and then, I think he later on got related to MIT, the electronics lab. That's where he puts his association still. Now this is, about Renaissance and Signition is that in 2010, George Zweig resigned from Renaissance, but this year, he has started his own hedge fund. So I think we wish him luck there. I think I read it in the Wall Street Journal. So he's the oldest guy to do a startup. So you see how remarkable that is. Okay, so that's about career side. The quark, or ACEs, as he was going to introduce to us, is of course his best known achievement, cochlea in a different circle. finance, which he does not really want to talk about, I think multidimensional. So I think because of the biology, CAD, Colloquia thing, and the Quark thing, when the MacArthur Foundation was first giving out awards, he received the first award in 1981. So that says something. He was elected to the U.S. National Academy of Sciences in 1996, and he's a fellow of the American Association of AAS. And probably belatedly, last year he was awarded the J.J. Sackright Prize, basically for theoretical physics. So I think it's a very illustrious career, and really it's my privilege, George, to give you the floor.
Thank you very much, George. That was a very kind introduction. Does that work? Can you hear me? No. Can you hear me now? No. Does this work? Does this work?
Yeah.
Yes. So let's get rid of this nonsense. There we go. Fortunately, I have two hands. There we go. That's good, thank you. Well, last year was the 50th anniversary of the discovery of quarks, and 40 years ago, it was the 40th anniversary of the development of quantum chromodynamics. Now, quantum chromodynamics developed in two phases. First, related to the discovery of quarks, and then the problem of specifying their interactions. Work in these two areas arose from two very different traditions. That of Rutherford and Bohr, which was very phenomenological and founded in an experiment, and that of Einstein, which was of a much more theoretical nature. The story really starts with the discovery of radioactivity by Henri Becquerel. This was just a few months after the discovery of X-rays. And Becquerel, who was interested in phosphorescence. Phosphorescence is this phenomena where you can take a mineral, expose it to light, and then later on it re-emits light at a different wavelength. And so Becquerel wondered if phosphorescent substances were emitting X-rays. So what he did was take salts of uranium and put them next to photographic plates that were covered with black paper, and then developed the photographic plates, and he would see images of these salts. And so he thought that in fact X-rays were being emitted. But one day it was cloudy, and he had this one. One day, like this? Okay. So one day it was cloudy, and so he couldn't expose the salts to sunlight. And he just put the salts together with the photographic plate wrapped in black in a drawer. And when a few days later he developed the paper, much to his surprise, he actually saw images of the crystals. And you see here an image that was taken later. Let me just get this going like this. You see here two images. One has the image of a Maltese cross, which you place between the photographic plate and the salt of uranium. Now, only 3 years later, Rutherford, who came from New Zealand, he was just a student, studied the radioactivity, these emissions, and realized that there were two different forms of emissions that were differentiated from one another by their penetration power, how far they could go into materials. And he called them alpha and beta. After Cambridge, after he graduated, he went to McGill, and there with a young instructor, Frederick Soddy, he investigated this phenomena of radioactivity. And as you can see from what's written over here, he says radioactivity, or they say, is a spontaneous disintegration of a radio element whereby a part of the original atom was violently ejected as a radiant particle, and the remainder formed a totally new kind of atom with distinct chemical and physical character. So for his work on radioactivity, Rutherford got the Nobel Prize in Chemistry in 1908, and Soddy got another Nobel Prize in Chemistry in 1921 for entirely different work. And in fact, 11 of Rutherford's students and collaborators, people in his laboratory, received Nobel Prizes. The story got even more interesting in 1908 and 1909 when Hans Geiger joined Rutherford's group and teamed up with an undergraduate, Ernst Marsden. And what they did was take these alpha particles that were being emitted from the uranium salts, and they let them impinge on thin metal plates, and they were going to study the scattering of these alpha particles off of these plates. And the results of their experiment is published in the Proceedings of the Royal Society, and here they say, in the following experiments, conclusive evidence was found of the existence of a diffuse reflection of the alpha particles. A small fraction of the alpha particles falling upon a metal plate have their directions changed to such an extent that they again emerge at the side of incidence. In other words, they scattered backwards. The interpretation of these results, which were totally shocking because no one expected that there would be this large backscattering. The interpretation was published by Rutherford 2 years later. And what he said was that the charges in the atom, see, a few years earlier, Thomson, in his discovery of the electron, showed that the atom was divisible. Before that time, it was an atom, but no one knew that it had parts. So he showed that it was divisible and that there were positive and negative charges, but the view was that they were intermixed with one another. And what Rutherford concluded was the only way he could understand the distribution of scattering of these alpha particles was to say that the alpha particles, in fact, were scattering off of point charges, either plus charges or minus charges. They didn't know which. And so that meant that the plus and minus charges in the atom were separated. But this was absolutely contrary to what was allowed by classical mechanics and also electrodynamics. Because if you had two charges separated and static, they would just pull together. And if they were orbiting around one another, then they would act like little tiny antennae and radiate emission and once again spiral together. The puzzle actually increased even further in 1914 where Marsden showed that the nuclei, that the positive charges were in fact themselves divisible and that they contained protons. And then the question was, what kept the nucleus, these positive charges, from exploding? Bohr came to visit, shortly after he got his PhD, came to visit Rutherford's lab in 1912, spent a few months there, and then spent 2 years from 1914 to 1916. And there he took two really incomprehensible ideas, that of charge separation in the atom, which was Rutherford's concept, and that of the quantization of radiation, which Planck had suggested, and he just combined these two incomprehensible ideas into a new single incomprehensible idea, that of stationary states. You see here Rutherford's group at Manchester University in 1912. And here's Rutherford himself sitting in the middle of the crowd. Let's see, over here you see Hans Geiger. This is Marsden. And this little guy back here is Chadwick. And there are other luminaries that we won't have time to go into. Now, as good experimenters do, they just keep pushing and pushing and pushing on their techniques. And so what Rutherford did, he and his students, was scatter alpha particles off of ever lighter elements. Ever lighter elements. It's very boring work. By the time 1927 came around, they had scattered off of hydrogen and also helium. And here you see a paper by Rutherford and Chadwick, where they say, the study of the collisions of alpha particles with hydrogen nuclei has shown that the force between the alpha particle and the hydrogen nucleus obeys Coulomb's law for large distances of collision, but that it diverges very markedly from this law at close distances. The experiments of Chadwick and Beeler showed that for distances of collision less than about 4 times 10 to the minus 13 centimeters, the force between the two particles increased much more rapidly with decrease of distance than could be accounted for on an inverse square law of force. So they had discovered the nuclear force directly. But in those days, physicists were very conservative. And they don't say they have a new force. You would think they would, because there's got to be a new force to hold the protons together inside the nuclei. But they're very conservative. I mean, these two guys are incredible. But their conclusion is that a possible explanation of the origin of these additional forces are discussed. This is in the summary. And it is suggested tentatively that they may be due to magnetic fields in the nuclei. Anything but proposing something radical. This comes from Cavendish Laboratory in Cambridge. Now, of course, the problem of the atom and how you think about it, at least non-relativistically, was solved in 1925 by Heisenberg and Schrödinger. The problems with the nucleus that you see here in this 1927 paper were not solved. I single out Heisenberg here because Heisenberg not only wrote down the laws of quantum mechanics, non-relativistic quantum mechanics, which was appropriate for the atom, but he also stated a way in which you're supposed to do physics. This is how you're supposed to think about things. You're supposed to only work with observables. He noted that prior to 1925, if people would have worked with observables, they wouldn't have been so confused. And later on, in 1943 and 1944, he published 3 papers talking about how one should approach the unsolved problem of the nuclear force. He said the observables there are just scattering amplitudes. And so the theory of high-energy physics should be formulated in terms of scattering amplitudes, the so-called S-matrix theory. And that idea was to dominate physics until the middle 1960s. Well, my first encounter with nuclear physics came in 1947. I was 10 years old. Every day after school, I would come home and listen for 15 minutes to a program called The Lone Ranger. And one day, the announcer said that if I would send in 15 cents and the box top of a breakfast cereal called Kix, you see the cereal here, send in this with 15 cents, and your address, self-addressed envelope, they by return mail would send you the atomic bomb ring. This was 2 years after the United States dropped the bomb on Hiroshima and Nagasaki. So I was pretty excited. I sent in my money. And I did, in fact, get one of these rings. The ring actually consisted of a zinc sulfide screen, which was the same kind of screen that was used by Geiger and Marsden. It also had a tiny little piece of radioactive polonium. And when you took this ring into a dark place, like a closet, which is what I did, and you pull off the cap, and then you wait until your eyes get acclimated to the dark, and you look down the long axis, you see these incredibly brilliant flashes of light. It was really, really spectacular. In fact, I was so impressed that I asked my mother to buy a second cereal, and I sent away for a second ring. I didn't know at that time that the lifetime of polonium is only 138 days. So I really didn't need a second ring. You see here it says, see genuine atoms split to smithereens. And then of course they say it's perfectly safe. The same year, in 1947, two particles were discovered, the pi and the k. The pi was expected because of the work of Yukawa, responsible for the nuclear force. The K meson was totally unexpected, and no one knew why that particle should actually be there. Just 2 years after this discovery, by the way, pi was discovered by Powell, who was another one of Rutherford's students. This thing is going on and off, isn't it?
Yeah.
Like this thing. I think that key is not
Okay, we'll try again. So only 2 years later, there's a remarkable paper that you see here by Fermi and Ye. It's titled Are Mesons Elementary Particles? And here in the abstract they say the hypothesis that pi mesons may be composite particles formed by the association of a nucleon with an antinucleon is discussed. By the way, at that time, no one had ever seen an antinucleon. It was just thought that such an object should exist. This got all that.
That one would always work.
Then I have to, okay. Oh, and I can't see. No, but I can't see the screen. Well, let's try this one. Does that work?
Yes.
You know, physicists are usually looked down upon engineers. Well, okay, now the motivation then for this paper is given in the first paragraph here. It says, in recent years, several new particles have been discovered which are currently assumed to be elementary, that is, essentially structureless. The probability that all such particles should be really elementary becomes less and less as their number increases. They only have a few particles and already they're complaining. These are very honest physicists. So here, right on the first page, they say, unfortunately, we have not succeeded in working out a satisfactory relativistically invariant theory of nucleons among which such attractive forces act. And this problem of how you build mesons out of nucleons and antinucleons was to haunt the field again until the middle 1960s. Although at the time that I was a graduate student, the people that were adopting this approach never mentioned this uncomfortable fact. Well, 10 years after I got the atomic bomb ring, I was an undergraduate at the University of Michigan studying mathematics, and I came across an article by Gell-Mann and one of the editors of Scientific American, Rosenbaum. It was published in the Scientific American. It was called Elementary Particles. Later on, I found out it was a rewrite of a more detailed article by Gelman and Rosenfeld, which was published in the Annual Review of Nuclear Sciences in 1957. In both of these papers, the authors say that there are two kinds of elementary particles. There are point particles, and there's two kinds, the leptons and the photon. And then there are extended particles, not point particles, which interact strongly. And they consist of the spin-a-half baryons, of which 7 had been discovered. An 8th one had been conjectured to exist, but had not yet been discovered. These numbers here, by the way, are the mass of the object in units of the electron mass. And then there were spin-zero mesons, and at that time there were also 7 of them found. Nowhere were resonances mentioned. So these are objects that are not necessarily stable, like the neutron isn't stable, it decays into, the neutron decays into proton, electron, and neutrino. But they have very long lifetimes. And so they're distinguished from resonances. Resonances live for like 10 to the minus 23rd seconds, the time it takes light to cross a nucleus. And then they disappear. And here you see, in the same issue that elementary particles were being discussed, there was a paper on resonances by Sam Lindenbaum. He talked about the total hydrogen cross-section, a plot of pi plus, pi minus plus proton as a function of a pion kinetic energy. And here you see evidence for a resonance, clear evidence, and then evidence possibly for additional resonances. These resonances had spin 3 halves, and they were called the delta or the 3-3 resonance. So you had in one journal elementary particles and resonances separate. And you had in the mind of all the physicists elementary particles and resonances, and they were all separate. They were not viewed in any way as having anything to do with one another. Now, in 1959, I decided to switch fields, and I left math and went to Caltech as a graduate student in physics. And after my first year there, first academic year, as summer came up, I went to talk to my quantum mechanics professor. His name was Bob Christie. And I asked him if I could work on some theoretical problem, because I really wanted to be a physicist. And Christie looked at me and with great contempt, and I quote you, he looks at me and he says, "You know nothing." This is true. And he says, "Why don't you go over to the synchrotron," which was an accelerator that was at Caltech, the highest electron accelerator in the world at that time, and learn experimental physics. And so I did go over to the synchrotron, and I talked to the people there, and I thought that the most interesting thing to do was to join an experiment that was going to be run by Alvin Talistrup. Alvin had this idea of a users group experiment. He thought that the days where people do experiments in their own accelerator at their own university were numbered. You go to another accelerator. And so I joined his experiment, and his experiment was to look at K plus goes to pi plus, pi 0 plus gamma. And I thought it would be interesting to do a different experiment. Look at K plus goes to pi 0 mu plus and nu. If you sit in the rest frame of the K plus, these particles are all in a plane, and if you measure the polarization out of the plane of decay, if it has a non-zero value, that means time reversal symmetry is finite. And that's an interesting thing. So I worked for a couple of years on that experiment. It was like a standalone piece. And we went up to Berkeley. We had 21.5 days of running. And when I came back, I had several 100,000 photographs. I started to look at them, and I didn't see any polarization. And it was very, very, very depressing. So I had this prospect of spending the next 2 years measuring all the errors and setting some kind of accurate upper bound to this decay. And I really didn't want to do it. So I practiced what's called denial. I just went to Mexico for, it must have been 1 or 2 months, just on a camping trip. And when I came back at the end of the summer, I had decided to switch to theory. Now, while I was working on this experiment, I had taken theory courses. And so I had some preparation. I had, on several occasions, talked to Murray Gell-Mann about Alvin's experiment, experiment K plus goes to pi plus pi 0 plus gamma. He had lots of students, and they graduated quickly, so he was the natural choice to be a thesis advisor. So I went in to see Murray, and I asked him if he would be my thesis advisor. And immediately he said, no. Then there was a long pause, and then he said he was going on sabbatical. So he would talk to Dick. And Dick was Richard Feynman. And I would never have had the courage to go in and see Richard Feynman and ask him to be my thesis advisor. So I waited for about a week, because I really didn't want to go in there. And then I had to go in there because Murray was going to talk to him. So I went in and I asked him if he would be my thesis advisor. He knew my face, but he didn't really know my name because I had sat in on a class that he had taught in general relativity. He was trying to quantize gravity. So when I asked him if he would be my thesis advisor, he said in a very low, professorial voice, he says, Murray says you're okay, so you must be okay. So then he tells me every Thursday I should come in at 1:30, and we would talk about physics from 1:30 until 4:15. At 4:15 we would adjourn for tea, and then we would go to the physics colloquium at 4:45. And we did this, I did this for the entire academic year. We never talked about any subject more than once, including, oops. You know what, I think maybe this thing is going off. So I might, oh, okay, so you know what I should do? I don't even know how to do this. This is probably going to happen again. I probably should go out and tell this computer not to go to sleep. I suspect it's sleeping, but I don't know how to do that. And I don't know what will cause more commotion. So let me keep...
Let me spend too long on the pitch.
Talk faster. So, in any case, we went through essentially all of theoretical physics and all of experimental physics. And I want to run through some of these topics so you get some feeling for what was going on at the time. We talked about axiomatic field theory, which was being practiced by Whiteman at Princeton and others, and it just contained no physics in Feynman hated it. We also talked about something that I call theory related to belief, and that was practiced by Jeffrey Chu. And in San Diego, in June of 1961, we have the following quote. This is from Chu, Jeffrey Chu. I believe the conventional association of fields with strongly interacting particles to be empty. Field theory, like an old soldier, is destined not to die, but just fade away. There was also theory related to experiment that dealt with classification. And in particular, there was a Cicada model, which was really the Fermi-Yang model that you saw before, but with the addition of another particle that contained another quantum number. He added the lambda. And I was very much attracted to the Cicada model. This idea of composites that Fermi and Yang had suggested was really very appealing. But the trouble was that the Cicada model gave you the wrong variance. You just didn't get the right particle spectrum. There was also classification. The particles that had been found were classified into irreducible representations of different groups. The most popular group initially was the G2. Fermi and Yang adopted G2, and Murray-Gell-Mann also adopted G2. But then as more evidence came in, Murray changed his mind and went with SU3, and Fermi and Yang still stuck with G2. There was also dynamics with no classification. Before we had classification without dynamics. Now we got dynamics. And I think the most beautiful example of the ideas that were present at that time, which were building on Heisenberg's idea that you should only work with observables, was this idea of the bootstrap. And this is from a paper that Fred Zachariasen, who was at Caltech at the time, published in Phys Rev Letters in 1961. He considered pi-pi scattering. Now this is a strong interaction, and so there's a particle that's going to mediate it. And he said, suppose this particle has spin 1, a rho particle. And at that time, a rho particle had been seen. So he said, suppose that that particle is exchanged between the two pi's. And let me look at the force between the two pi's in the p wave. So when I look at these two, when they're spinning around one another with orbital angular momentum 1, and they're exchanging a rho, I get an attractive force. So I get a resonance. And so I can write down the properties of that resonance in terms of the scattering or the exchange of the rho. And if I assume that the particle that's formed as a resonance is the same as the particle that's exchanged, then I can get relations, or I can compute what the rho pi-pi coupling is, that is what the width of the rho is, and I can also tell you what the mass is. And when he did this, he got roughly the right answer. So it's clear that this calculation, in some sense, had its heart in the right place. But I really didn't like the bootstrap because I didn't see how to bootstrap the pion. The same problem that Fermi and Yang had. In experimental physics, a lot was happening. More particles were discovered. Perhaps most importantly, the fourth lepton was discovered. So then there were 4 elementary spin-a-half particles. They also found the 8th spin-a-half baryon and the 8th meson, and that's what led to classifying particles into representations of SU3, because they had 8-dimensional representations. Most interestingly, 26 different meson resonances were found. This is just in a period of 2 years. The rho, the omega, these are all spin 1, the K star, and the phi. Well, one Thursday afternoon was especially exciting. I went in to see Firemen, and I told him about this paper, The Existence and Properties of the Phi Meson. Now, the Phi Meson was already known to exist. So that wasn't so exciting. It was what the phi didn't do that it was supposed to do that was interesting. So how many here know what a Dowitz plot is? Okay, so let me just say, let me not try to explain this. Let me just say that what we're doing here is looking at the results of an experiment. K minus plus proton goes to lambda K plus K bar. And if you look at the invariant mass squared of the KK bar system, you see an enormous peak. That's the resonance, that's the phi. The different shadings are the different modes corresponding to different charges on the K. So that shows you that something exists. It's really there, and it's very narrow. The surprising thing is that what you would expect is that this particle, which was called the phi, would go into rho and a pi. And the rho would decay into 2 pi's. So you would expect that if you looked at the mass of the 3 pi system in the same reaction, you'd have a big peak. But really, there was no peak that was statistically significant. So the phi was not going to rho pi. Now this was noted in the experiment that was published in Phys Rev Letters. The authors say the observed rate for phi goes to rho pi is lower than predicted values by 1 order of magnitude. However, the above estimates are uncertain by at least this amount, so that this discrepancy need not be disconcerting. Well, in preparation for my meeting with Firemen, I made my own estimate of what I thought the rate for phi to rho pi should be. And if you look at the branching ratio of kk bar to rho pi, it turns out to be the cube of the momenta of the final state particles. And since the rho and the pi have much more phase space, this is much, much bigger than this. So expected is a quarter. In other words, you should get 4 times as many rho pi's as kk bars. But you got greater than a factor of 35, which was observed. So I was tremendously disconcerted. I mean, this was unbelievable, because Firemen had taught me that in hadronic physics, everything that possibly can happen does, unless it's suppressed by some kind of symmetry. What sets the limit is unitarity. It's as strong as possible, subject only to the constraint of unitarity. And here there was something which was suppressed by 2 orders of magnitude, and there was no symmetry to account for. Well, Firemen was not impressed. So when he told me that when he discovered the V minus A theory, all the experiments were against him. And he says, forget the goddamn experiments. Just forget it. This is some kind of error. Just go on with your work. But I simply couldn't leave it alone because I thought that this was unprecedented. And eventually, the only way that I could see my way clear to this was by really extending the Sakana model and changing it a little bit. So like the Sakana model, I said, suppose that we had constituents, not the proton, neutron, and lambda, but something I call P0, N0, and lambda 0, isotopic spin doublet, and a singlet. And then we can make meson, and I call these things aces, for reasons I'll talk about in a moment. So the mesons are made out of one of these and the adding particle, AA bar. And if the spins oppose each other, then it's got spin 0, like the pi, the k, and the eta. And if they line up, you get spin 1, like the rho, omega, k star, and the phi. And for the baryons, you just have 3 of them, and as opposed to the Sakana model, which would have A, and A bar. And if 2 of the spins go one way and the other one goes the other way, you get a spin and a half particle, like the proton or the neutron. And if they all line up, you get something like the delta, that 3-3 resonance that I just showed you before in the resonance picture. So this comes from the paper, this figure, January 1964, where I show you the representation that I had of the vector mesons, which I call Deuces. So here's an ace, here's an anti-ace, and they're connected by a spring. Here we have the rho, the omega, the k star, and the phi. And what I've done is I've made the lambda 0 heavier than the others. And so I drew them bigger. So this guy has 2 of them, this guy has 1, and these 2 don't have any. And then I postulated that when a meson decays, the aces that it has flow into the final state. There's a conservation of aces. So in modern notation, this is the way it looks. Here's the A and the A bar, it's a meson. Over here we have another A and an A bar, a different A bar. And so here. And what happens is that the A and the A bar are going through space and they start to separate. And that polarizes the vacuum. And the polarization of the vacuum leads to the creation of a pair. And then that pair matches up with the A and the A bar and the original state to form the final mesons. So if you have a rho, this guy, that would be one of these guys. And here's a phi, that would be this AA bar. Well, it's got all these boxes in it. It's got lambda 0 bar, and the rho doesn't have any of those, so this thing can't go. So phi doesn't go to rho pi. Well, then I noticed that there was irregularity in the masses. And the masses obeyed various relations, and there was really a hierarchy. Some were more accurate than others. So what I said was that the mass of a hadron was the sum of the constituent masses, sum of this, plus the energies of interaction. Subtract off the potential. And the mass splittings were much greater than the energy of interaction. So, if all the masses were the same, all the particles would have the same mass. But if you made the lambda 0 heavier than the p0 or the n0, then you would get this relation. You'd have the rho and the omega would have roughly the same mass, and these are the masses, the mass squares that were known at that time. I use mass squares for mesons because of the Klein-Gordon equation. That involves mass squares, where spin-half particles involve masses. But that was just that was cheap. I just had to do something, and that's what I did. So in any case, these are